some vector operations previously in section 6.3, like scalar multiplication, vector addition, vector subtraction. One thing we didn't do is multiply vectors. So there are kind of like what we would consider sort of like two versions of vector multiplication. They're called dot products and cross products. So what we're going to look at today are the dot products. So here's our definition for a dot product. Suppose you have some vector u, and I wrote them in component form, u sub 1, u sub 2. So like that's my horizontal component and my vertical component for u. And I'll call my other vector v, so I'll have a v sub 1, v sub 2, horizontal and vertical component. The dot product, u dot v, is the horizontal components multiplied, so u sub 1 times v sub 1, so get a product of the horizontal, added with the product of the vertical components, u sub 2, v sub 2. And we read that, like usually we say u dot v, because there's a different version that kind of looks like multiplication, but it's got the cross. So we're looking at the dot product right there. What you'll get for your answer, like you'll get a product for u sub 1, v sub 1. You'll get a product for u sub 2, v sub 2. You'll add them together. It's just going to be a single number. So we would like to say that the answer is some scalar, like just some number. It's not actually another vector. And that's different than addition, subtraction, and scalar multiplication. When we did those things, they stayed vectors, right? They still had a horizontal component and a vertical component. With a dot product, we don't have a vector anymore. It's kind of like if you think back to matrices, that happened when we did determinants. The determinant was just a scalar number. Okay, so let's do an example. Suppose u is negative 6i minus 3j and v is negative 8i plus 4j. So I just want to kind of like, you've been practicing on your homeworks as well, but I want to like sometimes throw things in component form. Sometimes I'll throw them out as linear combination form. Remember, this doesn't mean anything different. We can still say for like u that our horizontal component u sub 1 must be negative 6, and our vertical component u sub 2 must be negative 3. So you can still say what's your horizontal and vertical components. We're going to find u dot v. So we take our horizontal component from u and v, multiply them, and add it with the vertical components of u and v. So that will be negative 3 times 4. So we're going to get what? Positive 48 and then plus a negative 12. So u dot v is 36. You okay with that? You got any questions about the dot product?
So we're not going to use like the vector numbers at all, so we're not going to use... Oh wait, never mind. That's right.
Yes,
How
Shane.
would we apply the scalar?
When would we use the dot product? So we are going to, in a couple slides, we are going to use the dot product to help us find the angle between two vectors. Okay, any other questions? Okay. You don't have to write anything down here necessarily. If you want to put like page 431, properties of dot products, just that like that exists in your textbook, you can. If you kind of just glance over these, they should make sense to you. Like if I do a u dot v, it would be the same as v dot u, because you're just like the multiplication of your horizontal and vertical components is going to be commutative, so it doesn't matter which way you multiply them. This is a bolded 0, so if you take a 0 vector which would have 0 horizontal component, 0 vertical component, and do a dot product with another vector, then both parts are going to be 0. So you get 0 as your scalar. This one kind of looks like our distributive property, so you might see that in the homework. Like it might ask you to do a dot product with the sum of u and v, or sorry, not u and v and w. So one way to do that would just be do the dot product of u and v, do the dot product of u and w, and add them together. Okay, 4 is kind of interesting. So I'm at least going to talk about that one real quick. So it says if you took a vector v and you did a dot product with itself, so I'm going to say v in component form is v sub 1, v sub 2. If I did a dot product v dot v, wouldn't I take the horizontal times the horizontal and it would be the same? So it would be like v sub 1 times v sub 1. And then I would do vertical times vertical, which would both be v sub 2's. And if you do v sub 1 times v sub 1, we could really write that as v sub 1 squared, and we could write this one as v sub 2 squared. Okay. So that's our dot product. Well, this v sub 1 squared plus v sub 2 squared should seem vaguely familiar to you. It's similar to the magnitude of a vector, okay? So if we did the magnitude of vector v, we have the square root of v sub 1 squared plus v sub 2 squared. So we're seeing that squared piece, okay? But notice the square root isn't there. So it's like we squared both sides. So this one just says if you do a dot product of a vector with itself, it will be your magnitude squared. Okay, so this dot product is equal to the magnitude squared. It's kind of just interesting to see how that works in terms of properties. Okay. And the last one is for a scalar. So C is not a vector anymore. C is a scalar. Notice that this is not the same as this distributive kind of thing up here. You distribute over sums or differences. But here you could just give the scalar to your first vector, so multiply it through u, and then do the dot product with v. Or you could multiply the scalar by v and do the dot product with u. The key here is you're not going to give it to both of them, because in multiplication, you just multiply two things together, and then you multiply by the third thing. Okay, so here's the one use of a dot product. Okay. We can calculate the angle between two vectors. So to calculate the angle between two vectors, you'll have cosine theta equals, and then notice the numerator says u dot v, and the denominator says magnitude u times magnitude v. So I'm going to kind of jot off to the side what this means. This is the dot product of u and v. And this is the product of magnitudes. That ratio of the dot product to the product of magnitudes is equal to the cosine of theta. So similarly, like what we saw for the law of cosines, is you'll get some ratio over here, some fraction, should be between -1 and 1. And then to actually solve for theta, you'll have to do the inverse cosine. So if you want to make a little note to yourself, you'll have to do inverse cosine to solve. I am fairly certain, and I will clarify tomorrow because we'll be working on our review, that this formula is provided for you on the quiz and the test. So you are responsible for other formulas related to vectors like the dot product formula, the magnitude, the direction angle, but this one is provided for you. Okay, so you'll see this on the quiz or test. You'll just have to be able to apply it. Quick note, it finds the smallest angle between two vectors. So, like when you inverse cosine, you're always going to get an angle between 0 and 180. So if I drew in two vectors here, put one in quadrant 1, and I'll put one in quadrant 2, it's going to spit out a number between 0 and 180 when I solve for theta. So it's giving the smallest angle between those two vectors. It's not giving this larger angle that's more than 180. So that could be in like any direction as long as it's the smallest angle. If the angle comes out to be 0 or 180, then you have parallel vectors. Okay, so it would mean that they're parallel to each other. It doesn't necessarily mean that they're going in the same direction. So if it's 0 degrees, it is the same direction. If it's the 180 angle, your vectors are going in opposite directions. And that should make sense. This one would look like they're on top of each other, so they're going in the same direction, pointing in the same way. This one, they could be parallel, but because it's 180, okay, it's a straight line, the other vector is going in the opposite direction. Okay, and then there's going to be some questions that may ask about a new word. But I think you have seen this word before in geometry. It's orthogonal. Okay, so you might want to put that down in your notes so that you're comfortable with it. It might ask you sometimes like, are these vectors orthogonal? Or give an example of orthogonal vectors. Okay. Orthogonal vectors are vectors that are perpendicular. So think about them as synonyms. I put this on the same slide as the formula for the angle between two vectors. So for two vectors to be orthogonal or perpendicular, what does their angle have to be? 90 degrees. Okay, so there has to be a 90-degree angle between the vectors. And let's just think about this in terms of this formula. Okay, so if I go up here and I'm thinking about I want theta to come out to be 90 degrees in the calculator. Okay, I'm going to be doing inverse cosine, right? And it's going to spit out a number between 0 and 180, but I want it to be exactly 90. The cosine of theta would equal what number so that theta came back as 90? What would your cosine have to be? What a ratio. Who said that? Haley says 0. Does that make sense? If your cosine is 0, you're going left or right, nothing on the unit circle. You'd be going up 1. 0, 1 is a point on the unit circle. And what is that angle? 90 degrees. So if we're thinking backwards, like to get an orthogonal vector to have an angle that is 90, then our ratio right here has to be equal to 0. Okay, this stuff has to equal 0 so that I inverse cosine 0 and I get 90 back out. What's the only way this fraction right here ever equals 0? If what part of it is 0? The numerator. The only time that your ratio of dot product to product of magnitudes will ever equal 0 is if your dot product is 0. 0 divided by anything is 0, right? So we can make a little shortcut rule down here. Vectors are orthogonal or perpendicular. And then I'm going to do an IFF. You remember that? If and only if. The dot product equals 0. Consider that like a shortcut to that question. If you're ever asked, like, are these vectors orthogonal, could I do the whole work and actually find the angle between the vectors and verify that it is 90 degrees? Sure, that would be a great argument. Angle between them is 90, so they are in fact perpendicular. But if you just want a shortcut way to check if they're orthogonal, the only way they'll be orthogonal is if the dot product is 0, so that you inverse cosine 0. So if you just check their dot products for 0, that'll be enough. Okay, make sure you have a calculator so you can try typing this into the calculator. We're going to find the angle between U and V. I think these are the same U and V's that I used before for the dot product example. So what did we say the dot product of U and V was on that first example? 36. Okay, we already know the dot product, don't we? Okay, I'm going to look for the angle between the two vectors. So the formula tells me to put the dot product in the numerator. Certainly you could calculate the dot product, but I'm using the same two vectors that we've already done, right? So I can just plug in 36. And then what else do I need to complete that? Magnitudes. So I'm going to have to go over here to U, and I'm going to do the magnitude of U is the square root of negative 6 squared plus negative 3 squared. That's 36 plus 9. So what is that? The square root of 45? Times the magnitude of V. So I'm going to calculate the magnitude of V. That's the square root of negative 8 squared plus 4 squared. So that's what? 64 plus 16? 80? You okay with that? Those are calculations from day one, right? You know how to do a magnitude, square root of v sub 1 squared plus v sub 2 squared? Yeah. Now, I did not simplify those, square root 45 and square root 80, even though they have perfect square factors, because it's not my final answer. Like, I'm just plugging those into a formula. So I'm going to be like undoing everything, so I don't really care if I have them simplified or not right now. Okay. So a couple different things. If you leave it as the square root of 45 times the square root of 80, what will you need in your calculator? What's that? Parentheses. Anytime you have plus, minus, or multiplication in the denominator, protect it with parentheses. You know, honestly, since they're both square roots, you could just do the square root of 45 times 80. Like, you could combine it because they're being multiplied. So if you want to eliminate that need for parentheses, you could type that into the calculator. I'm going to type into my calculator the inverse cosine of, and then I'm going to do 36 divided by parentheses, square root 45, I would have to close my parentheses, square root 80. Oops. Open a parenthesis right there. So something like that. Should get an angle between 0 and 180. Remember, these will be provided for you, or the formula will be provided for you, so it's a matter of can you plug in and actually calculate the answer. I got 53.1. Do you agree? Oh, can you show me what you have in? Put 95, that's 45 on the board, sorry. I know it looks like a 9. But it's 36 plus 9 over there. Anybody else having trouble with their calculator? You have the square root of 95. This is 45. Sorry. Okay, now just really quickly to kind of make a connection, I'm going to graph these two vectors real fast. U is negative 6i minus 3j, so from the origin in standard position, that would be 6 to the left and 3 down. So there's U. V would be negative 8i plus 4j, so somewhere in quadrant 2. And remember, this formula finds the smallest angle, so there's like two angles in between these two vectors, but it's finding the smallest angle. Does it look like that could maybe be a 53.13 with my quick sketch? Yeah, seems reasonable. Questions that you want to ask about? Okay, what if I asked you if these two vectors are orthogonal? Tell your group what you might do and then make that calculation. There's many ways to answer that. Are they orthogonal? Tell your group what are some things you could try. Any groups got ideas for us? What could we start with? Evan? Dot product. Those two vectors will only be orthogonal if what? If the dot product is 0. So it's like, is the dot product 0? Yes, they are orthogonal. Is the dot product not 0? No, they are not orthogonal. So I'm just going to do U dot V. That's when I take the horizontal components, multiply them, add the vertical components, multiply. That's negative 2 plus 2 equals 0. Are they orthogonal? Yes. Dot product equals 0. Could I go through the whole formula and calculate the magnitude of U and the magnitude of V and then multiply them underneath 0? Sure, but it's still going to be the inverse cosine of 0 at the end. So if you can just think about that whole process we went through, as long as the dot product is 0, then you have orthogonal vectors. Okay. Last thing that we're going to talk about today is the formula for work. So work has a formula. It is force times distance. Those of us coming from a physics background, we're familiar with this formula. You guys use a different word for distance. You say displacement. Is that correct? Or sometimes you do like change in x or change in y right there, right? Your little delta x, delta y, something like that. Okay. If you want to shorten it, you can say that work is equal to F times D. Okay. But here's the thing that I need to make clear for everybody who's coming, not necessarily from a physics background. Work is like what you put in to actually do a particular task. So like let's say I have a table up at the front or desk. I'm going to push the desk across the room, right? And we want to know what is the work that I put in to push the desk. Well, because I'm pushing the desk horizontally, even though I'm probably also pushing down on the desk and forward, it's the forward part of my force that matters in actually moving the desk horizontally. So that's where it says component force. in the direction of your motion. So if I'm pushing something or pulling something horizontally, I'm going to be using the horizontal component. Okay. If I'm like working on a pulley system, okay, or something like that, and I'm moving something vertically, then we're going to be focused on my vertical force. Okay, so you choose the force, the component force that matters to move this object, okay, or make this thing happen. Just as a quick side note, that's going to be magnitude times cosine theta, or magnitude times sine theta, for those of you trying to make the connections. So the stuff that yesterday I was like, find a vertical component, find a horizontal component of velocity or force, whatever that may be. Okay, you will pick which one applies to the problem. Okay. So this is actually an example. I don't think it's one of your homework problems, but it is. It's on page 439. It's number 84. So if you want to write something down about it, you can, or if you just want to write that problem. So if you want to go back and look at it. We've got a ski patroller. That's this guy right here. He's pulling a rescue toboggan right here across a flat snow surface by exerting a force of 35 pounds on the handle that makes an angle 22 degrees with the horizontal. So they've got that labeled. The 35 pounds is our force. Okay. And right now it's like our total force. So that is our vector, right? Like yesterday, how our total velocity was our vector, or our initial velocity, then that's our force. Okay. We want to find the work the ski patroller is doing to pull this toboggan 200 feet. So I'm going to do work equals F times D. D is your distance or displacement. How far is this ski patroller pulling our rescue toboggan? 200 feet. So D is 200. Okay. For force, we want only the component force that matters to pull this rescue toboggan in the direction that the rescue toboggan moves, which is which directions? Vertical or horizontal? Horizontal. It's a flat snow surface, right? He's pulling it horizontally. So we want the horizontal component force. So I can say that work is 35, the magnitude, times cosine 22. Okay, so there's my horizontal component of force, times my distance. And I say distance, you might say displacement.
So when you're deciding if you're going to use sine or cosine, horizontal is cosine and vertical is sine.
Yes. And then you just type it into your calculator. So 35 cosine 22. If your calculator opens a parentheses, make sure that you close it there, and then times that. Okay, so probably the biggest thing that's different for my physics, based on my experiences in years past, is the labeling. Because you guys in physics spend a lot of time using like joules and newtons and things like that, yes? Okay. So we just kind of like use the labels that we have, okay, in the vector. So like a mathematician, because we're going 200 feet and our force is in pounds, we call that foot-pounds. It's kind of like a strange label, but that's how we would name the force. It's like the two, like the distance measurement, and then like your pounds, or if you were measuring something different. So if you're coming from physics, maybe that's a little bit weird. Is that weird? I feel like it has been weird in years past. But to me, it's pretty like simple. You just name the two parts. Okay. Questions, concerns? If you're unsure if you're reading a problem and no picture is provided, try drawing a picture. Okay, we've got about 10 minutes, so I want you to get started on the homework so that you can ask questions.